¿Sí? Bien, buenas tardes desde hace unos minutos. Bienvenidos a todos. Vamos a tener hoy una nueva conferencia de este ciclo de conferencias de excelencia que estamos organizando desde CeiMar y en la que en esta ocasión pues nos acompaña y os presento al doctor Peter Ross del programa de investigación en contaminación del océano, que depende del acuario de Vancouver, del Vancouver Aquarium y del Marine Science Center. Esto es una novedad respecto a lo mejor al tipo de estructuras a las que estamos acostumbrados para instalaciones de este tipo, el hecho de que a la vez sea un lugar de divulgación, de comunicación con la sociedad, como es lo que tradicionalmente conocemos de un acuario, pero que a la vez tenga programas de investigación activos, y de hecho Peter Ross es el director de ese programa de investigación en polución oceánica. Él tiene un perfil académico e investigador pues muy notable, con más de 140 artículos científicos, es decir, que es alguien que está ahí a caballo entre en esas dos dimensiones de la investigación marina, por una parte la investigación formal y, en fin, con publicaciones en revistas de máximo nivel, y a la vez estar pendiente de programas de divulgación y de concienciación hacia la sociedad. Estuvo vinculado como científico al gobierno de Canadá entre los años 96 y 2013. De hecho, en una primera etapa formativa de él, pues coincidimos curiosamente no en donde está ahora en Vancouver, sino en Halifax y Dartmouth, en la costa atlántica de Canadá, en el Instituto Bedford. Y bueno, curiosamente hemos descubierto ahora que estuvimos a la vez en mi caso durante algunos meses y en el suyo durante un poco más de tiempo, pero simultáneamente estábamos en aquel instituto a finales de los años 80, hace ya demasiado tiempo. Bien, él estudia sobre todo contaminantes prioritarios de interés en el océano, y estudia tanto fuentes como transporte, destino y efectos. Ha participado en numerosas comisiones como experto acerca de regulación de contaminantes químicos, especies en peligro, salud del océano. Se ha centrado sobre todo en mamíferos marinos. Y bueno, luego dedica esa parte del trabajo pues a estudiar con comunidades aborígenes, sobre todo temas de alimentación tradicional. Actualmente también desarrolla una investigación intensa en el tema de polución por plásticos, en contaminación por petróleo, y dirige un proyecto de monitorización de la polución marina en las costas del Pacífico canadiense. La charla que va a dar hoy está muy relacionada con esa experiencia y bueno, se titula, como veis en la pantalla, Ocean Pollution in Canada's Oceans, Lesson Learned from Marine Wildlife. So, very welcome to our university, to our campus of excellence, CeiMar, and we are very happy to receive you in this. All the room is plenty of people. I was a little afraid about the exit of this talk. So, thank you again, and up to you.
Thank you. Buenos días. Habla la inglés? Everybody speaks English, which is good because my Spanish is not very good. So thank you for coming on a Friday. I'm sure there are other fun and interesting things to do today for you, but I will talk maybe for 40 minutes. If you have a question, you can certainly interrupt me, or you can wait until the end. This is informal. And I'm certainly happy to be here, so thank you to my host, Fidel. And I will talk to you about a fairly general topic. That's what I study. That's marine pollution or ocean pollution. I'm a toxicologist by training, which means I'm interested not only in the effects of pollutants on wildlife, but also where they come from, how they get into the environment, and where they go in the environment. Source, transport, fate, and effects of different contaminants. And when we look at the ocean, it's a big body of water. There are many oceans, and we have a lot of water out there, and we have a lot of pollutants, a lot of chemicals. So where do we start? And there are many government agencies and managers and regulators and scientists who look at their computer, their laboratory, their chemicals in their bottles, and they try to figure out, are they going to get into the environment? Or should I be worried about this? Does this present a risk to the health of humans, or does this chemical present a risk to an animal species, non-human? I prefer to do things a little bit backwards, and I like to let the species in the ocean tell me a story. In other words, I look at the marine mammals or fish or birds or invertebrates and let them tell me a story about which pollutants or which chemicals might be a problem. And you might think that that makes a lot of sense, or that we do a lot of this type of work. But the truth is, in Europe and Canada and Asia and the United States, we're doing less and less of this sort of environmental science and more of the applied science or industrial science. So this sort of work can be expensive, can be difficult, is in some ways perceived to be far removed from society and therefore not really very relevant, or it's too complicated. Please feel free to, there's one chair here, and there's maybe one seat here. Don't be shy, come on in, this is informal. Very, very Canadian. So what I'm going to tell you is a little bit about where I come from and why I think it's important and what it has told me about the state of our oceans and what we can learn, what we can take back to the regulators, the policymakers, the managers, the scientists, etc. But first, I have a test for the students of Spain. Actually, it's not really a test. It's a quick background on Canada and how much you know about Canada. How many people have been to Canada? Not very many, okay. Do you know it's the second biggest country in the world? 10 million kilometers squared. 36 million people, so fewer people than Spain, but much bigger country. 3 oceans, right? Atlantic, Arctic, and Pacific. 229,000 kilometers of coastline. Spain has about 5,000. So 229,000 kilometers of coastline. Most Canadians live in the far south. In fact, 80% of Canadians live within 100 kilometers of the border of the United States. So Toronto, Montreal, Ottawa, Vancouver, they're all fairly close to the United States. You might think of Canada as a northern country. It is. But it's also actually a fairly temperate country. In fact, if you look at the latitude of Montreal or Toronto, it's not all that far north. You look at Toronto is 43 degrees latitude north. That's about the Spanish-French border. So it's south of Paris. Montreal is about 45 degrees north. Vancouver is a little bit further north. It's 49 degrees, which is about Paris. Okay, so in terms of latitude, you shift over to where you would land in your airplane in Canada, fairly temperate, fairly southerly, shall we say. The furthest most southerly point in Canada is called Point Pillet, which is just over here. It's just under 42 degrees right here. And it is the same latitude as Northern California. So it's a big country. When I came to Spain, I flew Vancouver, Toronto, Toronto, Madrid. Toronto, Madrid was 6 hours and 30 minutes. Vancouver, Toronto was 5 hours and 30 minutes. It's a big country. 5 time zones. I tell you this partly to just make everyone relax and learn and have fun about where I'm coming from, but also because if you think about ocean pollution and you think about 3 oceans and 229,000 kilometers of coastline, you're dealing with some areas that are very remote and some areas that are very close to industry. This is my city right now, Vancouver. You may know it from the Olympics or just as a major tourist destination. It's a temperate rainforest. We do not get snow. Average temperature in January is about 10 degrees Celsius. Average temperature in summer is about 25 or 27. So it's fairly temperate, fairly moderate. We do get a lot of rain, October, November, December. It is a rainforest. We have those giant trees. We have salmon coming back. This is all part of the rainforest sort of environment along the coastal shoreline. So 3.5 million people in Vancouver. It's the biggest city in British Columbia, and it's the province, British Columbia, where I do most of my work. 200,000 Aboriginal people that have maybe 70 communities along the coast. The ocean is very, very important to Aboriginal people in Canada. Long history in that area of heavy reliance on the many and abundant salmon resources as well as other marine products. I work at the Vancouver Aquarium Marine Science Centre. You may think of an aquarium as a place for children to go visit. We are. We have 1.2 million visitors every year. They're very interested in seeing beluga whales or sea otters or jellyfish or turtles. We also have a tropical zone with marmoset monkeys and bats and all sorts of things. So it is a tourist destination. But it is not a company. It is a non-governmental conservation organization. So it's a non-profit entity, which means we make no profit. If you come and you pay a ticket to get in, the money goes back into the aquarium, and it helps support research and conservation. So it's very different from SeaWorld in the United States, which is very for-profit. They want to earn money. We don't want to earn money. What we want to do is have a good place to visit and learn. We want to do research that makes sense from an ocean perspective. And we want the visitors to go home and say, I'm going to do a better job as a citizen of the ocean to reduce my impact on the ocean or to protect the ocean. So that's kind of our rationale. I'm a scientist. I'm in number 2, research. But I have to do my research in support of communication and education, and hopefully in a way that helps protect the ocean. My program that I run is called the Ocean Pollution Research Program. It was launched in 2014. I actually worked for 17 years as a federal government scientist in Canada. My program, when I was working for the Government of Canada, was terminated by a conservative government. You know the politics in every country. There's conservative and there's more liberal or centrist or Democrat. We had a conservative government. They said, we don't want to study ocean pollution. We get rid of all the ocean pollution experts in Canada. So that was in 2013. Vancouver Aquarium said, hold it. We're worried about pollution. This is important. They brought me on, and I started this program. We're part of a new institute called the Coastal Ocean Research Institute within the aquarium. We're very, very excited about doing research with graduate students, with postdoctoral fellows, with staff scientists, in partnership with other universities, et cetera. The programs that I run within the Ocean Pollution Research Program, I've got them into 5 categories that you and I and everybody would probably be able to understand reasonably well. Marine mammals. I've done a lot of work on marine mammals. They provide an indication of the overall state of the ocean. Safe traditional foods for Aboriginal communities. The people of coastal British Columbia that predate what we call contact, the Indians, which we don't really refer to as Indians anymore. We call them First Nations or Aboriginal communities. Very strong connection to the ocean today, as well as before contact. We want to make sure that what they eat from the ocean is clean, safe, abundant, and we want to be able to speak using good scientific tools that make good cultural sense to Aboriginal communities. Hydrocarbons in the coastal environment. We're concerned about oil spills. The Prestige in Spain was a big oil spill. That's a catastrophic event. Hydrocarbons are always present in the environment. There are many natural hydrocarbons. There are hydrocarbons from your automobile or from the bus, from a factory, from street runoff, but also oil spills. So oil spills get a lot of media attention, but there are many, many other, sometimes much more important sources of hydrocarbons in the environment. We're trying to understand a little bit about that. Plastics and microplastics I'll speak to. You all know what plastics are. And Pollution Tracker is a program that we began, I'll get to in a minute, a couple of years ago to look at sediments and mussels to monitor coastal environmental quality. So these are the basic programs. And I wanted to introduce Carmen Morales at the back. She can wave at you. Carmen got her PhD from the University of Cadiz in 2007. I had to look that up. I thought it was... But she spent a year and a half with us. She's still with us at the Vancouver Aquarium. So she is a Spanish citizen, but she was working at the aquarium where she oversaw the design and launch of our pollution tracker project. That's looking at sediments and mussels as a standardized tool for monitoring environmental pollution. Sediments, right? That's mud below the surface of the ocean. It's a sink. It's where a lot of pollutants end up. So you can collect sediments. It's a very useful monitoring matrix, if you will. And mussels, the invertebrates that are filtering maybe 100 liters of water a day, depending on how big they are, they're also a very, very good monitoring matrix or species for a wide range of different types of pollutants. So Carmen was setting that up. And she also was there at the office the same day I arrived at the office when the news cameras were on our doorstep because there was a fairly minor oil spill in Vancouver Harbour on April 8th, 2015. It's the Marafasa pictured on the left. And so Carmen helped to oversee a lot of the sampling that we took to look at where the oil was going and collect those samples. Why? Number one, because we're in a position to do so and to use good scientific knowledge to collect samples and work with the appropriate laboratory to analyze those samples using the best available technology, so getting good high-resolution fingerprinting. But also B, because this spill happened right beside the Vancouver Aquarium. So our entire collection of fish, invertebrates, anemones, corals, marine mammals, birds, etc., was at risk because of this fairly modest 3,000-liter spill. But it's bunker crude, very nasty. There was a smell throughout downtown Vancouver. The very popular beaches, we have a lot of beaches right beside skyscrapers downtown, very popular for people running, swimming, walking with their dog, playing volleyball. There was all of a sudden there was goopy oil everywhere. It was visibly, it was not nice, but it was explosive in the media because Vancouver citizens are very proud of their downtown beaches. So when they smelled and saw and ran into this, they weren't very happy. So Carmen was involved in that and continues to be involved in that. So with ocean pollution, where do we start? I told you about the animals telling me a story, and this is a backdrop as to why I think the animals are very useful. There are now 100 million chemicals registered on the global marketplace. Can you believe that? 100 million chemicals. Do you think that we study every single one of those chemicals? Absolutely not. Only a handful, maybe 20 or 30 chemicals do environmental scientists sort of study routinely out in the environment. Over 250,000 of these are in common high production usage around the world, with 1,000 new chemicals every single year. And those chemicals are rarely investigated thoroughly before they're sold. There's very standard bits of information that a company has to provide to the regulators. But other than that, it's fairly free and flexible. When we think about where these chemicals are going to end up, we think about their properties, their physical and chemical properties. And my third bullet there, you can think of something that dissolves in water, and you can think of something that does not dissolve in water. So it's water soluble, or it's fat soluble, or particle active. How many people are in chemistry in the room here? Chemists? Major in chemistry? Oceanography? Biology? It's multidisciplinary.
Most of them are studying in the general type, so they are looking at angle.
Good. Multidisciplinary. Multidisciplinary. Great. Okay. So I try to categorize these contaminants or pollutants in fairly simple terms as being water soluble or not water soluble. And that's very, very important. Because once any chemical gets out into the environment, it has to make up its mind. Am I going to dissolve in water and move with water? Or am I going to bind to fats or lipids or particles, organic detritus, particle active? So that distinction is going to drive how they move through the environment, where they're going to end up. Okay? Very important. And of course, there are different receptors or species at risk. Depending on what type of contaminant you are, you're going to end up in different parts of the environment. If you're at top of the food chain, bottom of the food chain, filter feeder, short-lived, long-lived, plant, animal, all of these are different receptors, which obviously are exposed to different types of contaminants. And different types of contaminants are going to present different types of risks to all of those different groups of species. So understanding something about the receptors, very important. Ultimately, we're talking about a complex mixture in the real world. Very complex mixture. So that's where you start to try to figure out what are the animals telling us about what's going on there. With the animals that I study, sometimes I refer to them as canaries. They tell us something about the environment that they're occupying. You know the canary in the coal mine story. The canary was used in a cage in coal mines, mostly in the UK, but also in the United States and elsewhere, because the canary has a high metabolism and is very sensitive. So it's breathing the air to survive, as we do, but it would fall down either unconscious or dead when it ran into toxic levels of carbon monoxide, carbon dioxide, or methane gas. All of those are harmful or explosive to human in the mine. So the canary provided an early warning about the problems in the mine and saved a lot of miners from disaster. And it's interesting, the canary often died, but more recently, the last canary, by the way, as far as I know, was retired in 1979. Fairly recently, only about 30 years ago. 30 years ago? 25 years? I'm losing track. Almost 40 years ago. So the last canary was retired, but they started to create a controlled environment for the canary, so that if the canary fell over unconscious, he would get oxygen to resuscitate him. So they started making more friendly ways of taking care of the canary. The problem with the canary story for me is this last point. If the canary dies, it's going to be too late. So if we're going to wait for our sentinel species in the environment to tell us something about our mistakes, we may have waited too late. And that's what the regulators, the chemical managers in government tend to try to do. They try to predict where different contaminants are going to head so that they can create conditions or legislation or rules of practice or disposal to prevent harmful chemicals getting into the environment. So that's what you want to do. So often what I'm stuck with studying are the mistakes that kind of got out of control. But we still publish that and we still provide that information to managers and regulators, because if we've made a mistake, we do want to turn off the tap. The canary. So some of the canaries I've worked on, this is a very common one. It's called the harbor seal or common seal in the UK. It's the most widely distributed seal species in the world. It's around the entire northern hemisphere, from basically southern France up into the Arctic, in Atlantic, in Pacific. It's very commonly or widely distributed. It's found in polluted areas. It's found in remote areas. It's not endangered. It is top of the food chain. It's long-lived. It's relatively stationary. It doesn't migrate. So it gives us a good overview of the fish and invertebrates that it eats. It's about 30 different species in its diet. So very good sentinel species, and I'll show you that. The cormorant. There are different species, but I studied the double-crested cormorant on the Great Lakes, which are the 5 lakes, the big lakes between Canada and the USA. Completely wiped out by DDT, the insecticide, in the 1960s, 1970s. They've since recovered. So very good, top of the food chain, a fish-eating bird. Okay? Mussels. Again, we talked about filtering contaminants from the water, another good indicator species. Killer whales. Done a lot of work on killer whales, and we have different populations in the northeastern Pacific Ocean. You have a population right here as well. So killer whales, in some ways, a great canary, in other ways, a not so good canary. So maybe you can think about these different species and why one would be a good one for something and one might not be. Some are easy to work with, some are not so easy to work with. Some are very long-lived, which means they have a lifetime to accumulate contaminants. Some are much shorter-lived. Different reproductive cycles, different feeding ecologies. But if you start to understand the biology and ecology of these different species, you can tell a story about the pollutants. And it makes sense. It becomes logical. And you can start to inform those regulators and managers on what your canaries are telling them about the world around them. There's one more, I don't like to call them sentinel species, but the Aboriginal communities that rely so heavily on seafood along coastal Canada. So in the Pacific part of Canada where I live, 200,000 Aboriginal consumers. They eat 15 times, that's 15 times more seafood than the average Canadian. That means if you're looking at ocean pollution, the ocean the topic is 15 times more important to this young girl and to her family along the coast. There's still, even though post-contact, you may know some anecdotes, the history with Aboriginal populations in the New World is not always a happy one. A lot of disease, alcohol, violence, etc., and cultural conflict. The ocean is still very important. There's still a large importance attached to that subsistence collection of food, and so that's another thing that we study. When we look at pollution, there are different proxies that we can use to look at industrialization or sources, and one would be basically smoke or particulate matter. If we're looking at atmospheric pollutant, this is very, very important. The atmosphere is a way in which pollutants go from Cadiz to the Arctic, or from Southampton or Liverpool into the Arctic, or from China to get to Canada, etc. The atmosphere is what destroys our boundaries, our international borders, and creates a single planet. It does not take long for pollution to go from areas of high population density and industry into remote areas. And this is one of the challenges we face. If we're trying to understand and protect the planet, we have to understand what's happening to remote parts of the planet and then try to track that back to sources, which will be Eurasia or North America or wherever the contaminants are coming from. So the atmosphere is an easy way to point out where a lot of the industrial activities are going on. And this is just PM10, particulate matter of a certain size fraction in different parts of, mostly in the northern hemisphere. And if we look at some of the contaminants of concern, they all travel through the air. They're all emitted, whether it's PCBs or DDT or dioxins or flame retardants or metals. They are emitted and then they travel through the atmosphere. The left-hand graph, we call that a spaghetti plot. You can probably understand why it's called a spaghetti plot. Those are 10,000 back trajectories. It's modeled back trajectories from southern British Columbia. I'll point it out here. Right here. Back to Asia. Those are 10-day modeled back trajectories because we had air sampling stations in Western Canada. And we said, okay, we're measuring PCBs, pesticides, metals, dioxins, PBDs in these air samples. Is that air, contaminated air, coming from Seattle, Vancouver, Victoria, or elsewhere? And it turned out that over 40% of those air masses, that air sample, came from Asia, and it took about 8 days to arrive from China or Asia to our coastline. So it means that in British Columbia, the prevailing winds are from the west, and they pump contaminants at moderate concentrations because there's a whole dilution effect across the ocean. It doesn't take long, 8 or 10 days. The Inuit, or Eskimo, we call them Inuit now, people in Canada's Arctic are the most contaminated people on the planet. Did you know that? Highest levels of PCBs, DDT, dioxins, you name it. 10 times higher than anybody in this room, probably, or than me as a Canadian. Why? Well, because we're eating mostly supermarket foods. The Inuit in Canada's north are eating char, which is a salmon species, Arctic cod, ringed seals, beluga whales. There's still a very strong connection with the ocean, in particular in the north. And they're eating about 110 kilograms of seafood a year, which is about 25 times higher than the average Canadian. Okay? And as a result of two things, their reliance on seafood and what we call the grasshopper effect, that evaporation and movement of contaminants from industrial regions into our polar regions, we get this effect of contaminants moving up into the food web, being forced out of the atmosphere, into the water, up the food chain, up the food web, and into their food. Okay, so this is pretty important. And it takes 5 to 10 days to get from Chicago air, polluted air, up into Canada's Arctic. Okay? I'm just trying to give you a sense of geography and how quickly some of our activities can impact areas far removed from where we live or what we understand. And we tend to view the ocean as a sink for pollutants. It's a sink because that's where everything goes. Hydrology, fresh water flows down into the ocean. Human activities, everything tends to go down towards the ocean. our sewage, our wastewater, our industrial effluent, the runoff from our city streets, the smoke, as I just described. These things end up getting into the ocean, where each and every one of those different chemicals or contaminants has that choice. You remember the choice. It's going to dissolve in water, or it's going to attach to particles, or get into lipids, the fatty part of the bottom of the food chain, which you would find in bacterial cell walls or phytoplankton. And then you get into small fish, and then a big fish eats the small fish, and then a really big fish eats the medium-sized fish, and then there's a seal, and an eagle, and a killer whale, and a human. That's the food web. So if you're a fat-soluble chemical, you're getting into the food chain, and you're getting bioamplified or biomagnified up the food chain. At each trophic level, you know the term trophic level, each position in the food chain, you typically get a 10-fold increase in the concentrations of most persistent organic pollutants. Okay, 10-fold increase each level. The other thing that they can do, instead of binding to fats, is to bind to particles, which can then either be grazed or consumed, or they can be deposited out, because there's constant sedimentation and burial of contaminants and sediments in the ocean sediments. And in fact, if you take a box core, a sediment core, going down, and you take it out, and then you reconstruct the history associated with that sedimentation layer, and you look at lead-210. Have you learned about lead-210? The isotope lead-210, it's a way of dating the sediment core and looking at the different levels. And you can say, oh, there's 1947, there's 1957, there's 1967, here's 2014. And then you can look at the history of emissions for different chemicals: lead, mercury, PCBs, DDT, dioxins, etc. So sediments retain that history. But you also see that they're getting buried. It might be 0.5 centimeter per year or 1 centimeter per year. That's probably the best thing that can happen for a lot of these chemicals. They get buried. Because if they're not buried, they remain available to that food web. And this is what happens to, this is PCBs, polychlorinated biphenyl, used as an industrial heat-resistant stabilizing oil between about 1929 and late 1970s, magnifying or bioaccumulating in from invertebrates into fish and up into harbor seals. Harbor seals up here, salmon, hake, baby salmon actually are fairly high, and then down into invertebrates. So you see this great increase in PCB concentrations up in the food chain. But at the same time, you also see here this map. It's not easy to see, but this is Vancouver Island. Here's Vancouver right here, British Columbia, the mainland, southern Vancouver Island, USA just down here. This is sediment concentrations of PCBs. Just the red is higher concentrations of PCBs. See higher concentrations of PCBs near cities. So you get that sedimentation and loss of PCBs from the water. These chemicals don't break down. The half-life of PCB, a typical PCB molecule in your body, is 7 years. So if you take 1 gram of PCBs accidentally, it's going to take 7 years for that to go down to 0.5 gram in your body based on your metabolism. In marine mammals, we see different numbers, but these are very persistent. In the environment, they're not breaking down very, very easily. Bacterial degradation is slow. UV-based sunlight and its effects on PCBs and other compounds, very slow, very persistent. And what we found, based on biopsies collected from killer whales in British Columbia, a couple of interesting things. They're persistent, they're bioaccumulative, and they're toxic. But when we take biopsies from known individuals, we know every single killer whale in British Columbia. Did you know that? Another fact about Canada. Every single individual, there's a photo ID catalog. Oh, that's J22. That's a female. She was born in 1973. She has 3 calves, two of them alive, one of them dead. This is her cousin. This is her sister. We know all the individuals. It makes for a very powerful database. You get a biopsy, just a little biopsy, 300 milligrams, skin, a little bit of blubber. We find the PCBs in the fat, in the blubber, in the lipid, okay? And we're able to tell a story, a biological story. In blue are the boys, in pink are the girls. Gender-based science graphical representation here. The boys have higher concentrations of PCBs than the girls. Or the girls have lower concentrations than the boys. Anybody know why that is? Yep, to the calf, absolutely. Do you know what the fat content? Think about fat, right? Fat soluble, it's found in blubber, it's found in milk. The fat concentration of killer whale milk, anybody guess? What is cow's milk? Vaca leche. It's, what is it, 3.4%? It says it right on your milk container when you buy whole milk, right? 3 or 4%. It's fairly low. Marine mammals, 35%. It's like cheese, okay? The milk, very rich, very nutrient-rich, very good, very healthy for the calf, except for one problem. The calf, or the pup, whale, seal, is one position higher in the food chain than its mother. And that's a time when it's very sensitive. Its endocrine system is developing, its brain, its reproductive system, it's growing, its skeletal system. It needs a finely tuned balance of natural hormones. Do you know what PCBs are? Or a lot of the persistent organopollutants? They're basically hormone mimics. You've heard of hormone mimics, or you've heard of endocrine disruption. They often look like hormones, like thyroid hormone, like estrogen, and they can disrupt the natural estrogen or thyroid or metabolic system of developing animals. So when we talk about concerns about these types of contaminants, we're worried about their slow, chronic developmental impacts on the immune system, on the brain, on the reproductive system. They're not acute poisons. They aren't going to make you sort of turn green and die. They're slow. They're going to develop your growth, influence your normal growth and development. Another interesting thing from these biopsies, 3 populations I've got represented here. In the top, the northern residents. In the middle, the southern residents. The bottom, transient killer whales. They all eat different things. The northern residents and southern residents eat Chinook salmon. That's a high trophic level salmon species. The transients don't eat salmon at all. Oops, I thought I had an animation, but it's not there. The transients only eat marine mammals. They eat seals, whales, dolphins. These guys are the most contaminated marine mammals anywhere in the world, okay? Because they're high trophic level. They live to between 50 and 80 years, long-lived, and they have trouble eliminating these chemicals metabolically. Some of these killer whales were born in World War I. We have a female in the southern resident community near Vancouver and Victoria. She's 103 years old now, 103. Okay, so these are very high levels. I've got, if you're interested in numbers, the average male transient killer whale is over 250 milligrams per kilogram. That's over 250 parts per million. Your average concentration is probably around 0.8 parts per million. So they're about 300 times more contaminated than you are individually in the same weight of fat. Okay? So these are very high levels. And I talked about the persistence of these chemicals. We are predicting it's going to be not until the end of the 21st century that the levels in these whales are going to be down below a health effects threshold. In other words, that they'll be safe from only one chemical, and that's PCBs. In other words, we now see adverse biological effects, which we've documented and published, in killer whales because of PCBs. One chemical class out of the 100 million out there. And they're going to be affected until the end of the 21st century. That's when it starts to wake us up as to how much of an impact these persistent chemicals can cause if they're released without us knowing and not doing anything about it. There's some good news. I'm going to go through 4 quick reports on good news stories. And this is where some of the canary research has helped to shed light on what's going on. Pulp and paper mills. To create nice white paper, we used liquid chlorine. That was used around the world. Bleach to make nice white paper. Until it was discovered in the 1980s that was creating dioxins and furans. You've probably heard of dioxins. One of the most toxic contaminants ever produced by humans, never deliberately manufactured. There's 75 kinds. And when regulations were put into effect, I've got a graph here showing 3 lines. These are the concentrations of dioxins in sediment, in dark blue, and regulations started at the far left. In crab, that is the sort of medium blue line. Anyway, they're all tracking each other. And then the light blue line is the pulp mill release of dioxins. So dramatic response to the regulations and reduction in the release of dioxins, reduction in the contamination of sediments, and the exposure by Dungeness crab, which was a very important commercial species. This is a good news story. Discover a mistake, discover an accident, document it scientifically, and act. Harbor seals have told us wonderful things about the improvement in marine environmental quality for PCBs. And I would argue that PCBs, polychlorinated biphenyls, are probably today, and have been for 40 years, the most important toxic chemical in the Northern Hemisphere. These are the ones we're most worried about. And they've declined by between 5 and 10-fold over the last 40 years since we documented, since we acted, since we implemented regulations. So that's a good news story. PBDEs, these flame retardant chemicals were doubling every 3 years in our harbor seals. They were banned in Canada and pulled off the market in the US in around 2004. And we're seeing the level starting to decline again. This is good news. And DDT, which you all know about, DDT was what caused widespread extirpation of fish-eating birds because they were eating at the top of the food chain, exposed to too much DDT. DDT looks and acts sort of like estrogen. So it caused them to create thinner and thinner eggshells because of the disruption of calcium metabolism, and eggs collapsed. You can see broken eggs there. That's what happened. And once they were banned in Canada and the United States, you saw a decline in DDT. That's the left-hand plot. And in the United States, the bald eagle recovered. These are numbers of nests. Single pesticide wiped out bald eagles, herons, pelicans, falcons, all sorts of fish-eating birds throughout Europe and North America. It's a really big problem, 1960s, 1970s. Recovery. So these ocean canaries are, in my view, excellent scientific tools that have helped us to do a few things. Number one, to identify emerging chemicals of concern. Did we make a mistake? Number two, to identify certain species that may be at risk from different types of pollutants. Number three, basically as tools to look at source, transport, fate of pollutants. And then ultimately, this kind of science is feedback for things like green design, regulation, source control, consumer education and choices, and best practices by industry. How is my time? Fidel? It's no problem. I sometimes slow down. 10 minutes, okay. 10 minutes, okay. If you have to go, please don't worry. Just leave. I won't be insulted. I might just cry. I'm going to talk to you very briefly about a new pollutant. All right, this is a secret. Nobody knows about this pollutant, but I made a discovery about a pollutant, and I'm going to share it with you because I think it's really, really important. This is a pollutant that represents a significant conservation threat in our ocean. There are 25,000 of them, actually, in the family. Very widely used in consumer and industrial applications. Sometimes, like PCBs, they have endocrine disrupting properties. They can cause not only chronic, but also acute toxicity. And we've found these things everywhere we look. What am I talking about? Don't be shy. I think you know. Plastic. It's a big story. We were just talking about plastic before the talk. And we all know about plastic. We use plastic. Every single individual uses between 1 times their body weight and 4 times their body weight every year. We use and dispose of that much plastic. A lot of plastic. It's everywhere, right? This is plastic production until 2014. It's quadrupled in the last 15 years. That means 4-fold increase in 15 years. Big, big issue. And we also know it's a visible issue. We've known this actually for 40 or 50 years. There have been scientific studies. There have been beach cleanup efforts. There have been entangled marine mammals that we rescue. They're in fishing nets, so a bird has swallowed something. We've actually known about this problem an awful lot, right? The visible trash or debris or garbage. How many people have heard about the Great Pacific Garbage Patch? Twice the size of Texas in the North Pacific Ocean, a little bit further afield for maybe you, but it's a big visual problem out in the middle of the ocean. And this is what we see. This is the west coast of Vancouver Island in southern British Columbia. We have cleanups occasionally, but it's really hard to keep cleaning up when there's such a release of so much stuff. And the picture in the top right is in Southeast Asia, where there's a lot less recycling. Plastic. It's a big threat, visible threat. We have known about it. We know that sea turtles mistake plastic bags for jellyfish. They think it's food. Take it in. They can't clear it out. they suffocate or die. We have whales around the world dying because of nets. We have albatross out in the mid-Pacific skimming the ocean, picking up bright pieces of floating plastic, and then dying because they've got a stomach full of plastic. We have 1,000 sea lions on the coast of British Columbia. 1,000 right now alive that have nets around their neck or elastic bands. We try to rescue 1 or 2 a year. It's expensive, it's dangerous for everybody, including the sea lion and the crew, but really big visible issues. What we're now starting to realize, though, it's not just the visible stuff. It's the invisible stuff or the barely visible stuff. And this is where we're getting very, very interested. That's microplastics. How many people heard about microplastics before? Good. And you know then that the definition of microplastics is any plastic product less than 5 millimeters, right? That's sort of international agreement. There's no agreement on how small it goes because it can go down to the molecular size, of course. So really, when you look at microplastics, you're looking at a maximum common definition, but the minimum varies. 2 types, primary and secondary. Primary just means here's a primary piece of plastic. It's this casing for this computer or for the microphone or for your chair. Those are primary. They're deliberately manufactured, and they can break down. If they break down, they become secondary microplastics. So if we look at the ocean, what do we see? We see both primary and secondary microplastics. If you go down to the beach, you'll see some Coca-Cola bottles, plastic. You'll recognize it. That's a primary microplastic. You might see a nurdle. Do you know what a nurdle is? Anybody know what a nurdle is? These are nurdles here. Nurdles are those little visible pellets. They're about 4 millimeters, and they're commercially manufactured. So if you are a computer manufacturer and you go, hey, Dow Chemical, can you send me 1,000 kilograms of polyethylene? They'll send you nurdles in bags. But you find them all over the beaches. They're all sorts of different formulations, different types of chemicals, but the same size. You find them all over the beach, all over the world. All right, those are primary microplastics. And what we're seeing in British Columbia is quite staggering, and I'm going to talk about what I know most about, and that is our geographical area of interest where we're studying things. On the left here is a sample of filtered seawater, and what we see under a dissecting scope, a dissecting microscope. And there's a 1,000 millimeter, micrometer, that's a 1 millimeter bar. You see the bar in the lower right of the photograph? And you see, what do you see in that image, that field of view? You see a lot of crap, right? You see little black dots, and you see these long, spindly fibers, colors, red, pink, yellow, purple, green, black. So we see a lot of different things. And on the right is this map that goes 1,000 kilometers offshore into the northeastern Pacific from basically Vancouver. And that's Vancouver Island, so it's southern British Columbia, right against Washington State. And we see the highest concentrations in red, the hot colors, the lowest concentrations in pink, the cold colors. And then the in-betweens are blue, green, yellow. Highest concentration right here. And then followed by green here. This is Vancouver, this is Victoria, this is Seattle, all right? This is, basically 200 kilometers up and down. The lowest concentrations when you go offshore. Makes sense, right? Why does it make sense? Why would you expect lower concentrations of microplastics 1,000 kilometers offshore? I'm just speculating here. We assume it's because the closer you get to the shoreline, the closer you're getting to the source or the sources, right? Human activities, land-based activities. And what are we seeing on the left here? You see that picture? What are those little, like you can think about a Coca-Cola bottle breaking down into smaller and smaller bits. They might become chunky little fragments. But why are we getting these little threads, fibers, long, spindly, colorful things? Where are those from? Clothes. Very good. We think so. We think a lot of them are probably from clothing. You wash your clothes. You know what happens? I know you don't have as many dryers here. Every household in Canada, we have a washer and a dryer. How many people have a dryer to dry their clothes? Most people hang them outside? Here? Yep, good. Less energy. But in the dryer, have you ever used a dryer? You always have to take out the lint. Lint. You know what lint is? You get this mat of all the different fibers so your machine doesn't clog up and catch fire. The washing machine is doing the same thing, but it's going down with your water into the wastewater treatment plant and into the ocean. We think. We're working on it. We're trying to understand more. We find as much as 9,000 particles in a cubic meter of seawater in coastal British Columbia. 9,000. Okay? It's quite a lot. And 80% of the particles there are fibers. Zooplankton are eating fibers in the northeastern Pacific. 1 in every 20 of these two species, the euphosid and the scopopod, neocalanus and Euphausia pacifica, are ingesting plastics. Okay? They think it's food. They think it's a diatom or something, or filamentous algae of sorts. So this is a concern, because what it means is we may have a similar kind of impact that we've long recognized at the top of the food chain in birds, turtles, seals, whales. We know that's a problem. But now we're looking at the bottom of the food chain. There may be a similar problem to different species that are not so charismatic. Not so many members of the public care about zooplankton, right? But they're kind of, you guys understand how important zooplankton are. So if 1 in every 20 individual zooplankton that we sample and collect in the northeastern Pacific has fibers in it, or chunks of plastic, that's probably not a good news story. So the question then becomes, where are these things coming from? Where's the macro debris coming from? Where are the microplastics coming from? And do all of these things collectively? To what extent are they presenting a conservation threat to the different species, whether it's fish, invertebrates, or marine mammals? I've tried to talk about a fairly complex story, but I was always trying to relate it back to a fairly simple story, because I think it's easier to have a take-home message there. And the number of chemicals and number of chemical concerns may be large, but the concept is fairly simple. Pollution is fairly simple. It's a contaminant that enters the environment, causes harm, or presents a risk of harm. The three fundamental questions I tend to think of when I think about contaminants that I see in the environment. I want to know, where is it coming from? Where is it going? And is it harmful? Those are fairly simple questions, but they also have some profoundly scientific sort of connections. There are scientific tools to understand and document these, and have to be, we have to use good scientific methodologies to answer these kinds of questions in a way that inform decision makers. So thank you all for your time today and for studying our oceans.
Okay, thank you very much, Peter. It has been a very interesting talk. Now is time of a debate. If any of you have a question for Peter, please, if anybody asking a question, please use the microphone you have in the desk and press the switch on the lower button. Any question? Yeah?
So how is it that I work at an aquarium and that I do research at the aquarium? So there are 600 people that work at the Vancouver Aquarium. It's a fairly large facility. And there are probably 8 people that are scientists at the facility. And we have our own laboratory space. We have our own work, our own expertise. And I spend most of my time in the ocean, sort of dealing with samples from the ocean, up and down the coast of British Columbia, up in the Arctic, in the St. Lawrence River, collaborating internationally. So in some ways, we're sort of independent of the aquarium. The aquarium is an infrastructure. It is a facility. It has public visitors. We do research. What we always say is if you come in as a student and visit the aquarium, we want you to know that we're studying that species in the real world, in the ocean. And that what we're learning from that is helping protect that species. So we're very sensitive about a public aquarium simply being there for show and tell and tourism money. That's not our mandate, but we're sensitive to that. And we feel it's a very important duty to study those species and their habitat and protect those species in their real habitat. Otherwise, we don't see the point of having them in captivity. Yeah.
How do you quantify, if you quantify the presence of microplastic in the body? Do you quantify, or you just see the presence, acknowledge the presence of plastic?
Good question. One of the big challenges with the plastic field or the microplastic scientific research field is various methodologies across laboratory groups and across studies that have been published in the paper. So many different approaches. If you have seawater, it's fairly easy. You filter the seawater, what you retain, okay, maybe there's some phytoplankton, zooplankton there. You can clean that out or digest it or pick it apart. With biota, it's very different. If you have mussels or fish or animals, you have to look at it, you go, well, if there's microplastics in there, how do I separate it? It's not exactly a chemical extraction and analysis process. So we use a combination of techniques, including digestion, using an appropriate, it could be an acid or it could be hydrogen peroxide. We can do partial dissections. For example, with fish, we can take out the GI tract and then digest the GI tract. There are ways to desiccate and freeze dry. And then subsequently to grind these things up and extract. So different techniques depending on the species that you're doing. In terms of quantification, we're trying to do two things. One is count. And when I say count, it means count, 1, 2, 3, 4, 5, but also color, length or width or size, and some sort of visual categorization. And then the second thing we try to do is analyze the type of plastic. We have an instrument now in our lab called an FTIR, Fourier Transform Infrared Spectrometer. With physical infrared radiation, we can excite molecules and get a signature back, a heat signature back from a single particle, tiny plastic, that signature is compared to a library. It tells us 99% overlap with polypropylene, or 94% overlap with polyethylene terephthalate. So we can identify not only the size, et cetera, we can identify the putative chemical formulation as well. So.
Any other question? Yes?
First, I will thank you for your conference. And my question is, if in your laboratories they work about contaminants adsorbed to microplastics, and if they seem to be a vector to fish or to microorganisms?
Excellent question. There are two lines of thinking internationally in the scientific literature about the toxic risk associated with plastics or microplastics. One is what I call the structural toxicity or potential structural toxicity. If an animal swallows a piece of plastic and it stays in its stomach and it cuts the stomach or it blocks the stomach or it fools the animal into thinking, I'm not hungry anymore, I'm satiated. That's what I call structural toxicity. That's one thing. Okay? Suffocation or laceration or blockage or damage, acute damage. The second line of thinking is these plastics, they're made up of chemicals. They sometimes have additive chemicals like hardening agents. You know BPA? Bisphenol A is a hardening agent. Or phthalate esters. Phthalate esters are softening agents. They have dyes. They have different things added to them. And then finally, when these plastics are floating around in the ocean, they soak up pollutants from the ocean. So if a fish eats plastic, it could be exposed to any of those different mixes of chemicals. And they can soak up those chemicals. Lots of people looking at that. The evidence is vague right now because to do this in the real world is very difficult. It tends to be done in the laboratory. I've seen some decent studies that show that there can be uptake from the plastic in the laboratory and in certain very localized sites. If you take mussels, they're filter feeding and they're on buoys, on flotation buoys that have a particular chemical in it. You can see that signature. But I'm unconvinced that that route of exposure and uptake is more important than the natural alternative. For example, if you're a fish and you eat a piece of plastic that is this big, or you're a fish that eats phytoplankton of the same quantity, that phytoplankton could have 20% lipid in it, full of contaminants as well. So I'm unconvinced that plastic is a significant sort of conservation level vector for chemicals to biota. I'm prepared to be proven wrong. There are plenty of people trying, but your point is a very good one. There are two things we're worried about in terms of a toxic threat from microplastics.
Yes? Please, do you mind to use the microphone, please?
Apart from the research you do and all the information you combine, is there any political impact on after your studies? Like, would you be able to say, this is like a really dangerous plastic or something, and would it have any impact on the political field?
This is the kind of question that I would encourage all of you to keep discussing throughout your education, and also ask your faculty advisors or professors about this, because this is a really, really fundamentally important conversation for science students and for scientists. There are many in the older school of science, the more traditional view of science, that as a scientist you must be impartial, nonpartisan, apolitical, non-human. You should step back and look at the world around you and be as objective as possible. Okay? And that's really the scientific paradigm that we continue to operate within. That said, for me personally, I find that very difficult, because the nature of what I study are chemicals that injure or kill or harm species that we care about, whether it's fish that we eat, whether it's marine mammals that we love, whether it's whales that we go and watch as tourists. You know, so it's hard for me to simply say I'm going to study it and do nothing else. What I do say is the currency of a scientist is the scientific publication that is peer-reviewed and vetted and published and defended. That's the currency. And we have to keep that moving, because there is a threat to that currency as well. These online journals with limited or no reviews, published very quickly, as well as the internet, present dramatic threats to the integrity of scientific method. And I think you probably know what I'm talking about. But as a scientist, I still view our role as providing the best available scientific evidence and expert opinion, where you can interpret and speculate and sort of suggest there may be some concerns. There are always routes to be more closely aligned with kind of policy advice. And I think there's a role and a responsibility there. Certainly when we talk about global issues like climate change, it's really hard. If you're the world's top climate change expert, it's hard to simply talk about a sample size of one, our planet, we're doing an experiment, I don't care, we might all die, I'm not going to say anything about it. If you know there's a significant threat to the world, I think you should probably be articulating that, but based on your scientific understanding.
Any other question? Okay, I forgot to present in my first presentation to present Carmen Morales. Later, Peter has introduced her, but Carmen was one of our students in several years ago, and is an example of opportunities abroad. She has got a position. She has been working there with Peter. And I would like to make a question to her. Can I? And I would like you comment, many students in the room, your experience, and please think that Peter is not here. And tell us about your experience and about the things you learned here, applied in that work in Canada, if you want or can.
Well, hello. Well, I don't know if I'm the best example, because I've been
Carmen,
like...
do you want to speak in Spanish? I'm trying to learn some Spanish, so I encourage you to speak in Spanish.
¿En español? Vale. Bueno, que yo he dado muchas vueltas por el mundo, pero yo estudié ciencias del mar aquí en Cádiz y también hice el doctorado. Entre medias estuve fuera con distintos programas de becas en Italia, en Portugal, en Inglaterra, y luego cuando acabé el doctorado también estuve por Francia y luego Canadá. Por eso, no sé, siguiendo un poco los instintos, un poco según lo que quería hacer en cada momento y lo que me interesaba, de qué quería saber más. Acabé el doctorado y quería saber más cómo funcionaba todo a nivel más internacional, más a nivel de gobiernos, cómo se ponían de acuerdo. Entonces acabé trabajando un tiempo en Naciones Unidas. Luego, una vez visto eso, supe que la ciencia era, quería seguir con la ciencia, así que fue como acabé en Vancouver. Y no sé si por eso sí puedo dar consejos, pero desde luego seguir un poco lo que os interese, lo que os llame, moveros. Y a mí la Universidad de Cádiz me dio una base muy fuerte, creo, pero hay que abrir un poco la mente, conocer otros lugares y aprender, seguir aprendiendo siempre. Y creo que eso es lo que hay que tener siempre en mente y seguir un poco los sueños de cada uno.
Muy bien, pues perdona por el atropello, pero creo que era una experiencia útil al menos, ¿no?, para algunos de vosotros. Y quizás, digamos, desde aquí os animo a intentarlo, a buscar oportunidades que fuera las hay, que quizás en lo que tenemos que mejorar mucho, y en eso lo sabe ahora Carmen, es en dar oportunidades para volver, ¿no? Es ideal en el marco de una carrera científica pasar una temporada fuera. Lo que habría que ser es capaz de recuperar a gente muy bien formada después de unos años haciendo investigación fuera, ¿no? Bueno, perdón por el paréntesis. Any other question for Peter? Okay, so thank you very much
Thank you.
for your collaboration.